Okay, before we get too deep into how to use a binary tree to implement an ordered set, we do need to talk about some of the common terms we use when discussing binary trees. Some of them you've already heard me say, and you're going to hear a lot more, but let's define them so we can be on the same page. Um, so, you've already heard me say that in a linked list, each node has one successor, right? A linked list is linear. But in a binary tree, each node has up to two children. Um, all nodes don't have to have two children. Like, for example, 1 has no children and 7 has no children. But they can have up to two children, but not any more than that. A node that has no children is called a leaf node. And leaf nodes are kind of down here at the edge of the tree. And there'll be times when we talk very specially about leaf nodes, right? So in this tree, 1, 7, and 5 are the leaf nodes. A parent node is a node that has at least one child. And so, for example, 1 and 7 are leaf nodes. They have no children, right? There's nothing hanging off of them. So 1 and 7 are not parents. A leaf node can never be a parent. But 5 has two children, 1 and 7, and so that makes 5 a parent. And 9 has two children, so 9 is a parent of 5 and 15, or we could say that 5 is the child of 9, or 15 is the child of 9, and so on. And we might also distinguish which child it is. So for example, 5 is the left child of 9, and 15 is the right child of 9. If you've ever studied genealogy and you've looked at, family trees, then all of this makes, good sense. Okay, and then there are some more special nodes. The root node is a special node. Every tree starts with a root node. Normally when I draw a tree, I'm going to draw it kind of vertically on a page, and I'll always have the root node at the top. Okay, and you'll kind of see the tree form downward. So if I don't specify otherwise, you can just assume that node of the very top is the root node. Okay, but in general, the root node should be specified, right? If no other information is given to you about where do you start in a tree, and if it's drawn in a way that it's not obvious, then you need to be told what the root node is, and you should expect that in the definition of a tree. Okay, so the root node is a special node where it all starts, and everything comes down. All the children it has start at the root and then extend from the root. And then a node that's neither the root nor a leaf is called an internal node. Another way of saying that is an internal node has to have at least one child. It may have two children, but it has to have at least one. Otherwise, if it had no children, it would be a leaf. The root node could be an internal node, or the root node could be a leaf node. If the root node is a leaf node, then that means your tree only has one node in it. Looks like I might have duplicated. No, I just didn't hit next. Okay. So, how can we represent a binary tree in code? Well, it might look something like this. And this is just the node for a binary tree and nothing else. So I'll have this class called BT node. This is meant to provide some, symmetry with our list node object that we had before. But now our BT node, and we're just going to have it hold some integers for the moment. Our BT node has a left pointer and a right pointer, right? Because every node in a binary tree can have two children, up to two children. Okay, and then I have a constructor that'll initialize my data item, which is just an integer in this case, and will initialize my left node and right node. This should say null pointer instead of null, but they're similar in meaning. And so my constructor will allow me to make a new node and initialize the left and right side of it. Okay, so let's write a little bit of code that'll build binary trees equivalent to these shown below. Okay, so let's say I want a binary tree where the root is 100, the left is 25, and the right is 150. So what I can do is I can make these three nodes. So the root is going to be 100, so I make a new node, new BT node with 100. Note that since I'm using new here, that means I'm putting a node on the heap, which means I get a pointer back to the node, which means there has to be a little star over here letting me know that I'm going to store the reference to my heap object in a BT node pointer variable. Okay, so my left side is going to be 25, my right side is going to be 150. And then I just need to set the left side to be this left object and the right side of root to be the right object. And now my root pointer is pointing at a tree that's like the one I've drawn here, where the root is 100, the left side is 25, the right side is 150. Okay, how about another? Well, let's look at this tree. I could do this tree in a different way. And the previous one, I built 3 objects and then I connected them together. But I could also just use my constructor to do that assembly process. So here I make my node 100, and then as an argument to set the left pointer, I just pass in the result of calling new BT node with the value of 25. That's going to be my left side. Then my right side is going to be a new node that's initialized with 150. So I could consolidate my code down a little bit and just let my constructor do the work of hooking the nodes up to each other. And now here's a bigger graph. My root is 9, and then it's going to have 5 and 15 as its children, and then 5 has 1 and 7 as its children. And so now in my compressed form, I make my root node, which is 9. The left side is going to be 5. Its left and right are 1 and 7. And then the left side, the right side of 9 is 15. And so I've just written this all out as compactly as I can. And then finally, here's a different tree. This is kind of a weird tree in that there's nothing over here on the left. It's all going to the right. And so what I'm going to do when I build this tree is I'm always going to set the left pointer to be null pointer, but then the right pointer I'll initialize with a new node. So 100 will have 150 on its right, and then nothing on its left, and then 150 has 200 on its right. Okay, so this is just getting you some idea of like how we could build these trees. Now, this isn't normally how we're going to build trees, because what we want to do is implement a proper set. And so when somebody inserts something in my set, we'll insert it into the tree in the right place. When somebody wants to find something in the tree, we'll, or in the set, we'll look through the tree to find it, and so on. If somebody wants to remove something, we'll go in and we'll remove a node from a tree. These examples are really just to get you thinking about what does this node look like in C++ code, and how can I build these trees up by hand if I needed to. Okay, just a few more definitions. Ancestor nodes. A node's ancestors include its parent, its parent's parent, etc., all the way up to the root, and including the root. So for example, 9 is the ancestor of 1, 5, 7, and 15. And 7's ancestors are 5 and 9. And notice I described this in 2 different ways. In one case, I said, what's everything 9 is the ancestor of? And in that case, it's everything below it, right? But if I say, what are the ancestors of 7, then I have to go up the tree. It's like I'm following the edge of the arrows in the opposite direction. I go from 7 up to 5, and then from 5 up to 9. And since 9 is the root, I stop there. So 7's ancestors are everything above it. But the only things above it are in kind of a direct path up to the root. So you go from 7 to 5 and from 5 to 9. And so 5 and 9 are 7's ancestors. Note 15 is not an ancestor because I would have to come back down, right, to get to 15. So it's not, strictly speaking, in the pathway back to the root. And a subtree is the set of nodes starting at a node and extending to its children, its children's children, and so on. So for example, the subtree at 5 includes 1 and 7 and 5. The subtree starting at 15 only includes 15 because it has no children. The subtree starting at 9 includes the entire tree. Because beneath 5 comes the whole 5 subtree, and beneath 9 on this side is 15, and so the entire tree is covered by the subtree of the root. Okay, and then a couple of other concepts that we're going to use a lot when we talk about trees are depth, height, and level. Okay, so a connection between nodes, I'm just going to informally call this an edge. So like if 9 is connected to 5, then there's an edge between 9 to 5. And then if I want to know how deep a node is, I'm just going to count the number of edges between the root and that node. So for example, the number of edges between 9 and 5 is 1. So that means the depth of node 5 is 1 because I had to cross over one edge. Whereas the depth of node 1 is 2. All the nodes at the same depth in a tree form a level. So 5 and 15 are both at depth 1. So they form a level. We call this level 1. 1 and 7 are a depth of 2, so they form a level 2. And then a tree's height is the largest depth of any node. Since the largest depths here are the depth of 1 and 7 at 2, then we would say that the height of this tree is 2. It doesn't matter that there's a node over here, 15, that's only has a depth of 1, since there are nodes at a bigger depth. They define the height of the tree. Okay, so in summary, binary trees are made up of nodes with one parent and at most 2 children. There are many common terms we're going to use as we talk about algorithms on binary trees, like parent, child, root, leaf, internal, node, subtree, level, height, depth. It's important to know these terms. A lot of them make intuitive sense, and you probably just already know them. But some of them, their meaning is important, and we're going to use it a lot. And so you're going to want to review these terms and make sure you really internalize them, so you know what we're talking about and what we mean when we discuss some aspect of trees. So you want to review them and commit them to memory.